So I wanted to start by covering encryption and kind of the different algorithms that are used. Two of them in particular. We'll start with like a simple one. And basically what I want to do is I want to talk you through the algorithm, and I want you to encrypt something, and then we're going to decrypt it together. And so it'll be like you're exchanging a message with me, and I'm going to find out what the message is. It's kind of like a secret, like a magic trick. Like at the end of doing all this math, it's going to be like, oh, I also got 8, and your secret number was 8 or something like that.
So is this something that we should be able to do, and the listeners won't know what our code is?
Yes, your message will be secret the whole time, and then I'll say what I got by decrypting it, and you'll say, yes, that is my secret number. It's literally like a magic trick.
Oh, cool. So yeah, if you're listening along, you can try and guess my number, but you shouldn't be able to figure it out.
Yeah,
based on what we're saying in our conversation.
Exactly. So you're going to have a secret message that only you know, and we're going to. What's a little bit false in this conversation is that we're going to discuss the private and public keys, because I want to show how you generate them. So normally, and I'll try and keep it separated, like this is public information, this is what anyone can see, and then this is private information, which only one person can see. So we'll try and keep that separate as we record, but the listener will hear both public and private information. But the one thing I do want to keep secret when we get to it is your message that you are encrypting.
Okay.
So 2 algorithms I wanted to cover. The first one is Diffie-Hellman. Have you heard of Diffie-Hellman?
I think maybe only in reference to some sort of encryption. I know the name is what I can say.
Yeah. So I'm by no means an expert in any of this stuff, but I think it's relatively simple enough and easy enough to just have a conversation about, and the math is pretty straightforward. You will need a calculator though, so you can get a calculator out if you'd like.
Yeah, well, I think I have one on my computer. Will that work?
Can it do modular arithmetic?
Ooh,
that's the most complicated. Everything else is multiplication, but you will need to do like mod something.
Let me see.
Yeah, if programming would work easily.
Let me see if I can just run a Python shell.
Sorry, I didn't prepare you for this.
Let's see. Nope, yeah, it's fine. 85 mod 3. Yep, okay, there we go. I'm assuming 1 is the answer to that.
84 is a multiple of 3? I know, but I'm...
85.
Yeah, I think that's right.
Oh, gotcha. Oh, right, yeah, because the sum of the numbers is 12, so...
Proved it.
Yep, okay, there we go.
All right, good first test. So Diffie-Hellman is a little bit different. Diffie-Hellman, the way we're going to talk about it here, is not for encrypting a message. It's not like you can send a secret message using Diffie-Hellman. The Diffie-Hellman exchange is for me to confirm that I am talking to you and actually you, and not somebody who intercepted my request to talk. So it's kind of like a handshake.
Gotcha, right. So, yeah, so just out of curiosity, are these things relatively new, like since the internet, or are these like World War II or prior?
That's a good question. I'm not sure. I do know that the second one we're going to talk about, RSA encryption, that came about in kind of the early computer days. And I think it was originally like the US government, CIA or someone like that, NSA, figured it out, RSA encryption algorithms. And they quickly made it top secret and didn't share it, didn't publicize it. But then the RSA people, I think they were at MIT, mathematicians or computer scientists, did then figure it out also. And so it bears their name. But I think it was originally discovered, I guess you could say, in the US government somewhere. I'm looking up Diffie-Hellman to see.
Yeah. I looked it up on Wikipedia, the most accurate source. And it's saying that the British Signals Intelligence Agency had previously in 1969 used it, but it wasn't published.
I see the
later,
name's Diffie-Hellman published it in 1976. So yeah, like early computer days. Yeah,
and then they were patented in 1977. Cool. So yeah, okay. And the idea generally with encryption, right, is that I have some message that I want to send to you, and I want to make sure A, that I don't send it to someone else, and B, if someone else does receive it, that they can't translate.
So the Diffie-Hellman, what we're going to do is the A part of that, and then the RSA, the next part is the B. I don't know if you can use Diffie-Hellman to do B. I don't think Diffie-Hellman's enough to encrypt a message. What we're going to do is pass information back and forth, And then at the end, confirm that we both got the same answer to a math problem. And anyone that was listening in on the conversation wouldn't have been able to get the same answer without knowing other information that only you and I have. Got it? So we're going to say like, the answer is 6. And we both say, did you get 6? And then you say yes. Obviously we wouldn't say that, but like pass what we got. And then that's how we know that I am actually talking to you. And all of this is based on the general easy math problem one direction, difficult math problem the other direction. So it's easy to calculate, some number raised to another large number modulo a third number. Like you can say 3 to the 29 mod 17. That's pretty easy to just plug in and calculate real quickly. But if you had 3 to the x mod 17 equals 12, you can't figure out x, basically. So that's the crux of all of this. It's based on some math problem that's really easy to do one direction, but really hard to solve for the inverse of it. Not really the mathematical inverse, but, working backwards in the problem to solve for another variable.
Right, yeah. And that's kind of hidden in the modulo part of this, right?
So, go ahead.
By the way, the answer was 12.
Good.
3 to the 29
exactly. But if you were asked, 3 to the what mod 17 equals 12, what's 3 to the what? Like 3 to the x? What's x there? You're not going to be able to solve that.
Right, and especially if it's like
exactly.
really big numbers, like 3 to the 29, I don't even think is that big.
So there's two numbers that we have to agree on, and this is done publicly. So we both pick two numbers ahead of time. One's the prime modulus. So, when I said 3 to the 29 mod 17, 17 is the prime modulus. So it's mod some number that's a prime.
Okay. Should we say what
we should talk about mod
means?
Modular arithmetic. Sometimes it's called clock arithmetic. It's basically when you learned in elementary school the remainder. So if you divide one number by another number, what's left over? That's your answer to mod. So 3 times 4 mod 10. So 3 times 4 is 12, and then mod 10, divide 12 by 10, and you're left with 2. Yeah. So the answer to 3 times 4 mod 10 would be 2. Yeah.
Right. Okay. Yeah. So, and then the reason it's called clock arithmetic is it's kind of like that's what you're doing with a 12-hour
So if your clock
system,
went from 0 to 10, that would be the mod 10. And if you wrapped your answer of 12 around the clock, you would end up at 10, but then you'd have to go 2 more past that. So your clock would read 2. So your clock is the size of the mod whatever. So mod 10 would be a clock of size 10. Numbers going up to 10.
Yeah, so if you're American, you're very familiar with mod 12.
Right.
Up to 24.
I'm 5'10". So the mod part is the inches at the end of my height.
Oh, I was thinking the clock, but you're right with
okay, so
too.
That's the first one we agree on publicly. We pick a prime modulus. This example I said was 17. And then we pick something called the primitive root or the generator. So when I said 3 to the 29 mod 17, the primitive root is at 3. So whatever blank raised to some power, that's our generator. And something that's pretty important, but it's kind of a small detail. That prime generator should be, when you do the modular arithmetic, 3 to the 1, 3 to the 2, 3 to the 3, all of those numbers, when you do mod 17, you should get an even distribution of the results across all the numbers, 0 through 16. Does that make sense? Like, you shouldn't be favoring, 5, for example.
Right, yeah. So if I had, 3 to the x mod some number, I wouldn't want it to, more often than not, have the result of that math equation be 8 or something. Because if that were true, especially if it was way more common, then I could just guess 8 as the that's gonna, if I know that it's somehow I can figure out what the 29 is, I'm guessing, or the power is. Right. If we have that.
So we have our prime modulus, our primitive root. Those are published. Those are public. Anyone listening to our conversation could hear those things. So let's say the prime modulus is 17 and the generator is 3. like we've been saying. So I'm going to privately pick a number. I'm going to say 3 to that number mod 17. So I'm going to pick a number, and I'm going to raise 3 to that number and calculate mod 17 of that. Okay, I got my number. Sorry.
Okay, can you say that? Can you say that?
So
last
I pick a private number, and I don't tell you what it is. I don't tell anyone what it is, but I have it, and I'm going to say 3 raised to that number mod 17. So the generator raised to my private number, I'm going to calculate that modulo 17. So I have my number. I'm going to tell you what I got publicly. So my 3 raised to my number mod 17 equals 14. So your job is to pick another private number, any number you want. Stick to maybe 2 digits. Don't get too big. Don't get too small.
Right.
I mean, your computer does huge numbers, but just for the sake of us.
Right. Okay.
Mod 17. So 3 raised to your number, mod 17. Right. Tell me what you got. Cool. So
all right. I
have your public number. You have my public number. Somebody listening into this conversation has both of our public numbers, but we still have our private numbers. I don't know what your private number was. So what you're going to do is take my number and raise it to the number I gave you, the public one. Take that number and raise it to your power that you chose. I'm going to do the same to yours.
Okay, so all right.
Yeah, this is going to be a big number.
Woo. Yeah, I don't think I can read this number.
We should end up with the same number here. So the whole point of this is that we do this and then we both compare that we got the same thing. So at least, I have a number times 10 to the 24. Did you get something like that? Oh, you're on your computer, so you're going to have to count decimals.
Yeah. I see. Yeah, it's probably
okay. So
something to the 24.
Let's read the first digit. Is it a 4?
Oh no. Okay, wait. So let me make sure I did this right. You told me you picked a private number. Then you did that equation 3 to that number mod 17, and you told me a number, and that number. So you should take
14 and raise it to your secret number.
Yeah. Then I told you. Okay. Then I told you. I picked a secret private number. Did the thing. Gave you a number.
Oh,
which I said was 4.
I made a mistake. I think we're good here. Now we calculate that number mod 17. This is the number we should agree on. I forgot that last step. So we have to mod 17 this. Oh, I got an error.
Okay.
Yeah, I'm getting
I got a number. That power is a pretty big power. I could change my private number. I don't know that'll help. I think actually,
Wolfram Alpha should be able to do this.
I don't know.
Okay. I got 4. Yes.
I got 4.
Success. All right, I'm going to stick with Wolfram Alpha. My phone's calculator couldn't handle that. I'm guessing it couldn't go out that many decimal places to get a modulus 17.
Yeah.
Okay, so we both agreed that we got the same number after doing our little private math, public math. I still have no idea what number you picked for your power. You don't know what number I picked for my power, but we both agreed that the result is 4. And you can imagine doing this in real life, like with computers, that 17 would be hundreds of digits long. So there's no way, it's pretty easy for someone to guess, 0 to 16 and then get the right answer every once in a while. Because all the answers for that final answer is going to be between 0 and 16. So
yeah. So whatever your prime modulus is, like that's 1 minus that, that minus 1 is your distribution of guesses essentially for this final number that we chose. So yeah, if you choose a 100-digit number or something, or I don't know, then you have your options are almost 0 of guessing.
And the fact that we both got the same answer at the end of that, that you're pretty confident that the person you're talking to is actually the person who you think it is.
Right. So like stupid choice is choose mod 2. Right. Then
or 0.
The answer is always 1. Yeah.
Yep.
Yeah. So 50-50 shot. So that would be like the bad choice. So now you make it really big, and we will always get the same number. It's just now a third party is going to have an issue guessing.
The Diffie-Hellman exchange it's pretty simple, and it's not that hard to do. You pick two numbers publicly. We pick each one privately, raise one of the numbers, and then mod the other number, and then share it, and then raise the other person's number, and then mod it, and then we get the same thing. And it's kind of interesting to think to see why it works. Like, basically, I took your number and raised it to my number. So your number, to recap, is 3 raised to your secret exponent, mod 17, raised to my secret number. So basically, if I have mod something raised to a power, I'm multiplying a whole bunch of numbers that are mod 17. You can ignore that and just say, multiple mod 17s is still just mod 17, multiplying them together. So it's basically 3 to your number raised to my number. So if yours is y and mine is x, it's 3 to the y to the x, or 3 to the y times x.
Gotcha.
And then what you did was 3 to the x times y. So it should work out the same when you take the mod of 17. I mean, it should have worked out the same even without doing that, without doing the mod 17.
Right. We could check that if you wanted on Wolfram. Yeah. Maybe that was the issue. No, but we could just check the first few numbers. I think I take that back. I
don't think we should have gotten the same number with the mod 17. Without the mod 17.
Without it. Oh, okay. Right. Yeah, this is the one that there's like a color analogy for, right?
Both the Diffie-Hellman and the RSA have a color analogy, and I think the analogies are pretty much the same. But yeah, you have a private color, I have a private color. It's really easy to mix the private colors with a public color, and then if I have red and green, or if my private color is red and yours is blue, and we make the public color green, and I mix my red with green, and you mix your blue with green, and then we both mix.
So wait, let's walk through that. You mix red and green. I think that makes brown.
Additive or subtractive colors.
Wait. Okay. Let's just do like paint. Let's just use the primaries: red, yellow, blue. So
I don't agree that those are primaries, but that's okay. I don't know.
With paint, they are
subtractive colors. We get cyan, magenta, and yellow.
What? Oh, okay. Well, I don't know how those ones combine, but I know how red, green, and blue. Red.
Okay, we're going like elementary red, school colors. Okay.
Yes. Yeah. All right. So, So I have red. You have blue, and then the common is yellow.
I have blue and yellow, which makes what? Green. And you have red and yellow.
Red and yellow, so then which makes orange.
We exchange, and I take your orange, and I mix my blue with your orange.
Okay, and black. You get like...
we pick black, primary, so it's always going to end up black. but we can imagine, other colors, not necessarily primaries. And we would end up with some other color. We get the same other color. But all the person who's watching this exchange go back and forth is seeing is that one agreed upon color, which was yellow, and then the mix of my color with yellow and the mix of your color with yellow.
Right. Yeah, and like with colors, you could easily figure out then what the secret color was.
Right. But in general, not necessarily. Like the person wouldn't be able to fake the mixture of the colors. Even though, so this is the reason they use colors is because it's really easy to show mixing colors, but it's really hard to say, given a color, what is it made up of? Like given a swatch of paint, like what colors make up that paint?
Right. Yeah. So yeah, if you use something other than primary, so primary is like, I feel like it's like selecting like the mod 2 example. It's not the best choice here, but it illustrates kind of what's going on.
So that's Diffie-Hellman.
Okay, so then this lets me know I'm talking to Derek and Derek
because
is talking.
We both got the same mod 17 at the end. And so we'd say, let's trade answers, and we trade them. And then I see that it's a 4 and you got a 4. So perfect.
Cool. So, but we don't know if somehow there's still someone in between us.
Exactly.
Intercepting our, because after this, so now I go, okay, I'm talking to Derek. Then I start sending you, the secret passcode to get into my house or something. I don't know. But then someone else is listening and they hear that passcode, they write it down. And
so we need to encrypt the actual message now, which we haven't done. So that's where, at least what I'm talking about, that's where RSA comes in.
Okay.
This one's quite a bit more complicated, the math, like the number of steps involved and the reasoning behind it. But it is going to, I think, be more interesting than we both get the same answer. It's going to be, you have a secret number that I don't know what it is. I'm going to do the algorithm, and I should say my answer is this. And then you'll say, yep, that was my secret message. So the simple, just basic steps of what's happening here is you come up with a message, M.
Okay. By
the way, we're going to have some variables here, because we're going to have to refer to things and say them in an equation. So your message M is going to be some number. So a 2-digit number, I think, keeps it simple.
Sure.
And then I'm going to generate a public key, a private key, and a product of 2 primes.
Okay, public key, private key, product of 2 primes.
Yes. So this is what, if I was doing this in real life, I would publish my public key.
Okay.
And the product of 2 primes is also part of what's public.
Okay.
Sometimes they refer to the public key as having, like, there's a number that I'm calling the public key, and then the product of 2 primes is also public. So sometimes they lump those 2 numbers together and say, that's the public key. It's those 2 numbers.
Right. Okay.
But what I'm going to refer to as the public key, we'll call the letter E as an egg.
Okay. E is public key. All right.
Right. Product of 2 primes is N.
Okay, so we only know I only get the product.
Exactly. So this is why people are all freaking out about, prime factorization. Is all this rests on the ability to factor factor a number into 2 primes. And obviously you pick very large primes.
Right.
But I'm not going to pick that big of numbers.
Yeah, you're going to pick something like 15.
Yeah, exactly. Yeah. That's not prime, but that's okay.
Well, it's a product of 2 prime.
Oh, yeah. And then I have a private key, which is a secret number that no one knows except me.
Does that have a name?
D, the letter D.
Okay, D is the private key.
Yeah, and I'm following. So most of the stuff, the Diffie-Hellman and the RSA content, I got from a YouTube channel called Art of the Problem, which I recommend people check out. They have some good videos. And this person used most of these variables, and then I did some other research. Wikipedia has a decent example walkthrough, and I looked up other places that pretty much all use the same variables. So
is it because it spells the word mend? No, I just looked at my notes here, and I just see down the side of it mend, and I was like, huh.
Well, we're gonna get C in a second in here. Okay. So C mend C. I don't know.
C mend doesn't sound like a great name.
Yeah. So we have your private message. You have my public key, a private key of mine, and product of 2 primes, which is N.
Right. Okay.
And then what you're going to do is calculate something called C, which is going to be your message raised to the public key.
Okay.
Modulo N.
Okay.
So you're going to calculate, basically you're going to encrypt your message using that procedure.
Okay. So do you want
M to the E mod N.
Do you want me to go ahead and do that?
Well, I need to give you the...
Oh, right. Yeah, I need E and N. Yeah, so I need a public key and a product of 2 primes.
Yeah. But what I'm doing now is walking through the steps that we're going to do, because calculating E and D is actually quite a bit of work.
Oh, okay. All right.
I'll give you E. E is not difficult to come up with, but I'll show you how I do it. And then D actually takes a little bit of work.
Okay.
So what you're going to do with E is say M to the E mod N. And then you're going to calculate your encrypted message, which is C.
Right. Okay.
And then what I'm going to do, you're trying to send me an encrypted message. So you would look up my public key and the product of 2 primes, encrypt your message, send it to me. That's that C that you just calculated. I'm going to take that and raise it to my private key.
Okay.
And when I do that, I'm going to end up with your message M.
Okay, so then I'm guessing somehow your private key is related to your public key and your product of primes.
Exactly.
Okay.
Yep, exactly. Okay.
And this is based on the same principle, I'm guessing, of a easy to check problem, but a hard to guess problem.
Exactly. Yeah. It's still using modular arithmetic, and we're going to use a function that is also really easy to calculate, but very hard to reverse engineer to see what generated the result using that function. Well, I'll go over that when we get there.
All right.
And by the way, I'm following the Art of the Problems YouTube video, which, as I understand it, followed the original RSA paper pretty closely, and other sources, including Wikipedia and modern RSA encryption, uses something slightly different, and I'll talk about that when we get there. But this is kind of the general, easiest to talk about function that we're going to use.
Yeah, because I've seen things like RSA 128 and RSA 256, and like I don't know if that matters or not, but I feel like I've seen like different versions of RSA.
Well, I think the 128 and 256, that's the bit size of like the encryption, the keys basically. Okay. Like how large the keys are, how large the prime numbers are that you're multiplying together.
Gotcha.
But there are also different standards for RSA encryption that use different function. Okay, so what I'm going to do, which is false, you would not see this happen, is I'm going to talk about my prime numbers and show you how I'm generating my public and private keys. So in general, the only thing someone listening to our conversation would see would be the public key and the product of two prime numbers and your encrypted message. Those are the only three things that would be able to be listened to by anyone following this.
Yeah. So they can see C, N, and E.
C, N, E. Exactly.
Okay.
Yep. So what I'm going to do is talk through how I generate the public and private keys. And so you'll see what your computer is essentially doing when you're getting ready to accept an encrypted message. So I'll pick two primes. They usually use letters P and Q. So I'll pick 23 for P, the first prime. And how about 11 for Q?
23 and 11. So I think I know how you're going to calculate N.
Yes.
Which is 253.
N is 253. So that would be public information, the first thing that's out there. 253 is known. It's not that hard to separate into its prime factorization, but you can imagine if these numbers got really, really large, it's really hard to figure out what the two prime numbers are that generate it. If someone handed you 253 and asked you what two prime numbers multiply together to give you 253, maybe you could figure it out, but it's not that simple.
Right. Yeah. So, you could sit there and do it. It would take you a while. It would take a computer even less time, but you start picking numbers that are like, 2 to the 57 minus 1 or something. You're starting to get, I don't know if that's a prime number, but, get those really large primes, then it's much harder to guess.
Right. So the next thing I'm going to calculate is something called Euler's totient function. Have you heard of that? Totient, not quotient, with a T.
I have not.
It's a symbol phi. It's a function of like phi of n is what we're going to calculate.
Okay.
And it's basically counting up how many numbers less than n, so phi of n. So how many numbers less than n are what's called co-prime with n, meaning it doesn't share any factors with n, essentially.
Okay.
So 10, for example, you would list all the numbers, 1, 2, 3, all the way up to 9. You don't count 10, but you do count 1. And you say how many of those numbers don't share a factor with 10. So 1 always counts for all numbers.
Right.
2.
In this case, it does.
It does. So 2 shares a factor with 10, namely 2. So we don't count 2. So we have 1, and then we have 3. Doesn't share any factors. 4 shares a factor.
Right. Okay. Yeah, 2. Right.
2.
Okay.
So we have 1 and 3. So far, phi equals 2. So we're just counting how many numbers there are that don't share a factor. So we have 1 and 3. And then 5 doesn't work for us.
Yeah,
right?
Namely 5.
5 shares a factor with 10 itself. So we have 1 and 3. 6 also doesn't count because it shares a factor of 2. So we still have just 1 and 3. And then 7, we do count 7. No factors with 10. So we have 1, 3, 7. There's 3 of them so far. 8 doesn't count, but 9 does count. So we have 1, 3, 7, and 9. So phi of 10 equals 4. There are 4 numbers less than 10 that are called coprime that don't share a factor.
Okay. Yeah. So that's, I feel like I'm seeing 2 interesting things, or maybe. So like even numbers, if you have phi of an even number, then you're eliminating like half of the numbers immediately.
Right.
The other thing is phi of a prime is what, 2 or 1, because it just has the 1, right?
No, opposite. All of them count.
Oh, yeah, right. Sorry, yeah, the other way.
Yeah. So that right there, that's an important thing. Yeah, we're counting the ones that don't share a factor. So for a prime number, all of them don't share a factor.
Right.
So for 11, for example, 1, 2, 3, 4, all the way up to 10. We don't count 11 itself. So phi of 11 is 10. Cool?
Yep. Yes. Right.
So phi of any prime number is the prime number minus 1.
Right.
So that's the first important step. By the way, this is another one of those easy to calculate in one direction, but almost impossible to go the reverse direction. So given 5n equals 862, what is n? That's basically an impossible problem to solve. Like, what number has 852 coprimes less than it? So we're going to take our n, which is a product of 2 primes, and we need one other rule for that phi function, that Euler's totient function. The first rule you already said was phi for a prime number is the prime number minus 1.
Right.
So the other thing is phi of a product is equal to the products of the phi.
Okay.
So phi of p times q is equal to phi of p times phi of q.
Right. Okay. Yeah. All right.
So I'm going to calculate phi of n, which is 5p times q, because n is a product of 2 primes.
Okay.
And we already said that it's going to be equal to p minus 1 multiplied by q minus 1, because p and q are both prime.
Right. So
this is something, you're picking 2 primes, you calculate n and share it, and then you have to do some other stuff. This is the first step, is working out this this totient function from Euler.
Right. So,
and we're going to be using another Euler theorem in a second using this totient function.
So when I did this, I said, okay, so I said our 2 numbers that normally no one else would know, or at least I wouldn't know, are 23 and 11. So the phi of the product is 523 times 511, which is 523 is 22, and phi of 11 is 10, like we said. Multiplying our phi of 253 which is our product, is 220.
Exactly. So the totient function of my product of primes is 220. That's not shared anywhere. That's just a private internal calculation that's done. Okay. The next thing I want to do is find so at this point, this is where I find my public key.
Okay.
I want a small prime number, maybe not prime, but odd, definitely, that is not a multiple of phi. Maybe that's not the word I'm looking for. I want phi divided by e to not be an integer. What's the math term for that?
You don't want to be mod 0.
Yeah, I don't want mod 220 to equal 0.
Yeah, I'm not sure I'm sure it's something really easy and we're just not thinking of it.
A multiple? I don't know. Factor?
Yeah. You don't want a number that is a multiple of 220. Because if it was a multiple of 220, then 220 goes into it evenly. Is that what you're saying?
No, other way around. So let's say my private key is 3. I don't want 220 divided by 3 to be an integer.
Okay.
Sorry, public key. I don't want my public key, say my public key is 3. Let's say it's 5, because this is going to be a bad example. So say my public key I pick to test, I say it's 5. 220 divided by 5 is an integer. I don't want that. I want something else.
Okay. Or so yeah, you don't want a number that is a factor or a product of factors of 220.
Right.
I don't know if there's a general name for that.
Yeah, I know. I'm failing at that too. So this is going to be my public key. So let me try 7. 220 divided by 7 is what? Should be something with a remainder.
Yep, a 1. Oh, wait, no. Sorry, I missed a number there. 3.
Okay, so I'm going to pick E, which is my public key. I'm going to say it's 7.
Okay. So there's a bunch of these numbers for our given totient number.
Right. I'm free to pick.
And you can just pick any of them. Okay, all right.
Right. Okay, so I publish E and I publish N. I put it out there. I put it on my email signature. I put it on my website. Put it on my Twitter bio, whatever. And then anyone can now encrypt a message using N, which is 253, and E, which is 7. Encrypt a message and send it to me.
7. Right, sorry. For some reason, I said 3.
We could have picked 3, but I just wanted to be adventurous and say 7. Okay, so I send you my public key in N, and then you calculate your message raised to my public key mod N.
Okay.
That's your encrypted message.
All right, so do you want me to... right now, we can just walk through an actual number ahead of time, and then at the end, we can...
Yeah, so do a pretend M, a pretend message.
Okay, yeah. So like I could pick 28.
Okay.
And so I do 28 to your public key, which is 7, mod that product of primes, 253, is that right?
Right.
63, which is probably just 28 then. Oh, wait, no, okay, no. All right. Yeah, so the answer is 63 is my encrypted message.
Yeah, so we're calling 63C.
Yes.
So do you want to do it with your actual message so we can keep the magic alive?
Well, yeah.
Or do you want to just say 28 was your message and it won't be as much of a magic trick?
Well, I was thinking for the final magic trick, we could do this without you giving me. You could just give me a product of primes. You could give me N and.
Oh, we'll just do it quickly just to recap.
Yeah. Without walking through how you created your public key or anything.
Right. We'll just see it all done in one step or shorter steps.
Yeah.
Okay. So C, which is the encrypted message that's passed to me. So you send an encrypted message, 63. What I'm going to do is raise 63 to my private key, which I'm about to calculate. This is actually the most involved step. And then mod N, and I should get your message back.
Have we talked about your private key?
Nope, we haven't touched it yet. I just sent the public key just so you could do something with it.
Okay.
And normally my computer would have calculated the private and public key first, and it just stores the private key somewhere. But just to give you something to do.
Right, okay, gotcha.
After I did my heavy lifting on the public key, which is actually not even the hardest part. So let's do the private key now, which is a little bit harder. And that private key, we're using the symbol D to represent the private key. Okay, I'm going to calculate my private key such that your encrypted message raised to the private key, mod N, gives back the message, mod N. That private key, by the way, it has to be independent of your message and your encrypted message. Like it doesn't depend on your message.
Right, yeah. Otherwise it'd be kind of useless.
Right. So the first thing we're going to be using is something called Euler's theorem. With respect, you can call it Euler's totient theorem. Some people call it Euler's generalization to Fermat's little theorem. So it has multiple names.
I feel like as soon as you say Euler's theorem, the follow-up question has to be which one?
Right, exactly. Yeah, just looking up Euler's theorem is not enough. I would say if you want to look it up, Euler's totient theorem. So what Euler's totient theorem says is take M, raise it to 5n. That's always going to equal 1, mod n.
Okay.
As long as M and N are coprime.
As long as M and N.
As long as the message and the product of primes are coprime.
But is there a way to guarantee that?
Well, we picked N to be the product of primes. And essentially the odds of your message being one of the primes in that product is non-existent.
Right. Okay. Especially if you're picking large numbers.
Right. So my 5n is, or my n is the product of two enormous prime numbers. And then the odds of your message being one of those two enormous prime numbers is basically doesn't matter.
Right. Okay.
So we're going to take your message, raise it to 5n. And that's always going to equal 1 mod n.
What is that? What does 1 mod n mean? You're either getting...
It's a remainder of 1 when you divide it by n. So m, your message, raised to that phi function, that number, whatever it is, divided by the n that's in that phi function is always going to be a remainder of 1.
But what is 1 mod anything? Is that always?
Well, it's like 12 mod. Oh, I see. Maybe I'm saying it wrong. It's not 1 mod n. It's not like, don't do that calculation. It's like 1 and then in parentheses modulo n. I should say it better. M raised to the phi n mod n equals 1.
Okay. All right.
I think I was saying it backwards.
Okay. All right. Yeah. Because I was like, 1 mod anything is 1 always, isn't it? It was what
right.
I was.
How
I was interpreting it. So that's not.
Sorry.
Okay.
It's like, the end of the sentence is phi, m to the phi n equals 1 when you're modulo n.
Okay. All right. That whole equation mod n, is that right?
That's right. Exactly. Yeah, thanks for clarifying that. I actually got hung up on something like that earlier, and I forgot to change it. So your M was 28.
Yes.
That's your private message.
Right.
And again, I'm calculating my private key, but what I'm doing is showing how you're going to end up with your message.
Okay.
So why don't we not use numbers right now? Let me just basically what I'm going to do is prove it, and then I'm going to use the proof, a step in the proof to calculate the private key, and then we'll go through and actually do it. But I want to show you and the listeners how it works first.
All right, let's
starts with Euler's totient theorem. So m phi n mod n equals 1.
Okay.
What I want to do is I want to raise both sides to some power k, and I'll show how to pick k in a second.
Okay.
So I have m raised to the k times phi n.
Right.
Mod n equals 1 to the k, but that's just 1.
Right.
K is an integer. I mean, doesn't really matter in that example, but it is going to be an integer. How do we pick k? We want k to be a small integer that gives us basically k times phi n plus 1.
K times, phi n plus 1.
All of that over e.
What do we want that?
We want that to equal an integer.
Okay, equals some. Sorry, k is equal to phi n plus 1 over e, or?
No, we pick k such that k times phi n plus 1 over e
is equal to some other integer.
Some other integer.
Okay.
Right. Because if we didn't have the k, if we had phi n plus 1 over e, that might not be an integer. So we're basically finding a k to give us an integer in that that function.
Yeah, because, we need this to be some multiple of 7, in our case, or some multiple of e. So we essentially will just increment by k until we eventually get there.
Exactly.
Okay.
So phi of n is... Basically, I'm going to start counting up from 1 and see what k gives me an integer.
Okay.
So I'm going to have k times phi n plus 1 over e. So k times 220 plus 1. So k times 220 plus 1 over e, which is 7.
Which is 31.5. So not an integer.
Right. So how about 441? Oh, so if k equals 2 times 220 is 440, plus 1 is 441, divided by 7
is what? 63.
Perfect. Awesome. So for us, we can stop right there. K equals 2.
And is this part of the theorem that there will always be some k?
Yep. That
will make this true?
Yes.
Okay.
Yep. And it all in the later step, you'll see why we needed an integer. But for right now, it's just a middle step is finding k to give us an integer value for k times phi n plus 1 over e should be an integer.
Right.
Okay. What I want to do is end up with m, not 1 on the right side. So right now, I'm looking back at my Euler's theorem, and all I did was raise both sides to the power of k.
Okay.
And then I looked at something else to figure out what k should be. But what I have right now is m raised to the k times phi n mod n equals 1.
Right. And that's m to the product of k times phi n.
Yes.
Mod n. Okay.
Correct. So what I want to do is get an m on that right side. So what I'm going to do is multiply both sides by m.
Okay.
So m times m raised to the k times phi. What does that do?
Adds 1 to k.
Yep.
Or k plus 1.
So I end up with m raised to the k times phi n plus 1.
Is equal to?
Mod n equals m.
Right.
And again, just to remind us where we're headed, I'm trying to get my private key.
Okay.
And we're going to bring D in a second.
All right.
Good so far?
Yep. So yeah, we found some integer k that gave us another integer based on this equation. Then we raised our Euler's-Tauschent theorem equation to that power. Then we wanted our message on the right side, so we multiplied everything, both sides by our message, and that gave us what we have now, m to the product of k plus 1 times phi of n, mod n is equal to m.
Right.
Our message.
Yes. So what I want now, I want to remind you what we're eventually going to do. I'm going to take your encrypted message,
okay,
which is your actual message raised to my public key E.
Right. Mod n.
Mod n. And I'm going to raise that to my private key D, which we're trying to calculate.
Okay.
So what I'm going to end up with is m raised to the E times D mod n. You with me so far?
M to raise to the product of E times D mod n. That's what you said, right? Yes.
Yep. I want that to equal your message m.
Okay.
So what does E times D have to equal?
It has to equal k plus 1 times phi of n.
Wait, how'd you get that?
By looking at our other equation, right?
Well, but let's look at, before we get to that other equation.
Oh, okay.
Let's look at that one equation. M raised to the E times D mod n equals m.
Right.
So what's the simplest thing that E times D could equal?
1.
To make that true.
1. Yeah.
So basically we want E times D to equal 1.
Okay.
In other words, my public key is the inverse of the private key, which, algorithmically makes sense. You encrypt it and then I decrypt it. So it's like an inverse operation.
Right. Okay.
Mathematically, we can say the product of those two things should equal 1.
Yeah. Okay. So to say what we have there again without using variables is we have the message raised to the public key times the private key.
Exactly.
And so public key times private key, we want to be 1, which is what you're saying
right.
They're inverses. Okay.
Yep. So we started with Euler's theorem, and then I'm trying to head towards this encryption and decryption. And so Euler's theorem with a couple modifications with that k and then the plus 1. Basically, I want m to the stuff. I want all that stuff to be E times D.
Right. Okay, that's what I jumped to.
Yes, exactly. Yeah. So E times D is equal to k times phi n plus 1, which means my private key is equal to k times phi n plus 1 all over E.
Sorry, wait. I might be. Oh, yeah. Okay. All right. Sorry. I may have said some stuff wrong earlier because I wrote this thing down wrong. So it's k to the phi. It's okay. Sorry. The power here is k times phi of n plus 1. Exactly. I think what I said was k plus 1 quantity times phi of n.
Right. No, what you first said was correct. Right. What you just corrected.
Yeah. So if in the past, and I'm pretty sure in the past I did say k plus 1 times phi of n, that's wrong. Yeah. Okay. All right. So it's m to the k times phi of n plus 1. Gotcha.
That's right.
All right.
So I want E times D to equal that. So D, my private key, is equal to k times phi n plus 1 over E.
Oh, hey. So that is just our integer that we got, right?
Which integer?
The integer that we got when we chose k.
Yes, exactly. So the whole reason of choosing K to make that product an integer exactly was I was looking ahead and I knew where we were headed, and I needed something to get us D to be an integer.
Gotcha.
And I had to introduce K first because logically going from Euler's totient theorem to the next step, to the next step, to the next step, I needed a K before I got the 1 in there.
Right. Okay.
So again, this started from Euler's totient theorem, which has been shown to be true. But then I want to end up with the actual message when I carry out some mathematical operations, not 1, which is what Euler's totient theorem says. And not only that, I also want to have a private key that's an integer. So I needed to modify it by raising both sides to K and then multiplying both sides by M.
Right.
Because Euler's totient theorem says it's equal to 1, but if I multiply that by M, I get my message back out.
Okay.
So now I have my private key.
So when you generate this, though, you just essentially generate your private key by doing the K times phi of n plus 1 divided by the public key E. You just keep iterating K till you get an integer, and then you say,
exactly,
that's my private key.
Exactly. That integer is my private key.
Okay. And then all the stuff we just did showed, hey, that's these two things are equal. This is why we're doing it, essentially.
Exactly. Yep. So we already actually know what it is. We already said it because we were checking when K equals 2. What is K times phi n plus 1 over E? But let's just say it again. K is 2. So we have 2 times 5n, 2 times 220, which is 440. Plus 1 is 441, and then divided by the public key, which is 7.
And that gives us our private key of 63. Yep. Or your private key.
D equals 63. Yeah, D equals 63. So I picked 2 prime numbers, multiplied them together, calculated that totient function, picked a public key, and then how did I decide my public key?
Your public key... I had it written down somewhere. Oh, okay. So yeah, you found, you took our product of primes, you did the totient function on it, and then you just had to pick any number, any coprime of that value, right?
Right. Yep. So basically take 5n and divide it by your public key and get something that's not an integer.
And yeah, anything that satisfies that can be your public key.
Yep. And then the private key was based on Euler's totient theorem, which had a bunch of stuff equal to 1. We did some changes to end up equaling M and calculate our private key. So I now have public key of 7, private key of 63.
Do you think it's weird? Sorry, I don't know if this will matter. I don't know if this will matter if this is pure coincidence, but my message was 28, just as a quick reminder. My encrypted message was 63. And our private key is 63. Is that just pure random?
I think it's random because the private and public key don't depend on the message at all.
Right. So we just got some weird luck there.
Yeah, we just happened to end up with that. So let me now decrypt your message, and I should end up with 28.
Right.
So you encrypted it, and you got 63. Your message of 28 raised to my public key of 7. Mod the product of primes n. So 28 to the 7 mod 253 equals 63.
Right. Yep.
That's your encrypted message C. So I'm going to raise C to the D. I'm going to raise your encrypted message to my private key and calculate that mod 253. And I should get 28.
Yep. Yeah, 63 raised to the 63rd power, mod 253 is indeed 28.
Amazing. Works. RSA encryption. So I wouldn't have known your message was 28, and I would have just done this blindly, and then all of a sudden I get your message. And you can imagine, you're typing an email and you want to encrypt it. Those letters and all those symbols are turned into a number somewhere in binary, and then this encryption happens on that number that is your email.
Yeah, we use I think they use UTF-8 or 16 encoding or something, or ASCII or whatever.
And there's a couple changes that happen in actual RSA encryption. They don't use that totient function. They use a different function that's related. And they use a different algorithm to basically, it doesn't rely on totient theorem or Euler's totient theorem. They use different things to do that calculation that speed up the process. So what we just did is the original RSA version, but they've since found other ways that are faster for encrypting and decrypting things.
So yeah, what is necessary for that function? For like a replacement function, it's just that it has to be such that the end result of encrypted message raised to private message or private key is mod n is the message.
Yeah, essentially, yeah. But there's another theorem that's related to Euler's totient theorem that's actually more straightforward, and it's quicker computationally.
Right. So should you give me a public key and a product of two primes?
Yeah, let's actually do that. I'm going to pick a new P and Q and then tell you N. I hope those are prime numbers.
Damn semi-primes. You didn't pick 51, did you? It always gets me 51.
Okay, my product of two primes, my N is 481. So I'm calculating 5N, and then I'm figuring out my public key. Okay, so N is 481, E is 5.
Wait, sorry, what is N again?
481.
Okay, so I thought, all right. And E is 5?
Right. So you could be listening and trying to factor 481 into two primes and see what they are. And
so I take my secret message and I raise it to your public key, and then I modulo that by N. And I pass that to you as 181. Then do we do a countdown and say the number so they know we're not cheating?
We should. What's your encrypted message?
181.
181. I'm trying to calculate my private key. Okay, I got my private key. 181 raised to my private key mod n, which is 481. All right. So I'm going to do 1, 2, 3, say the answer.
Okay, all right.
Ready?
Yep.
1, 2, 3, 90. Yeah. Cool. It worked.
Cool. So we can pass secret messages. Nobody knew that secret message until that moment.
That's right. Yeah, someone asks your age, you're like, I'm going to encrypt that so that no one else can hear.
Yeah.
Let me know your public key and your product of two primes, and I'll get it to you in about 5 minutes.
Yeah. Wait. I've got a question that I'm trying to follow along here. So I know the public key. I know the product of primes, which is 481, and okay, all right. Here's the problem. Okay, all right. I was trying to figure out. I was like, I know the equation to generate the private key. Why can't I just generate your private key off of 481? It's because when we did it, we said, we need to know phi of n, but the easiest way to do that is to take phi of p times phi of q.
Right.
And I don't know what p and q are. I just know 481. So yeah, I mean, presumably I can there's probably Wolfram Alpha. I could probably type in totient of 481 or something to give me a value.
Yeah, I just did it, and it spit out the right answer.
But if n is super big, I'm guessing it must be really hard for a computer to calculate that.
Right. Yeah, and you would imagine there's tables of phi for products of primes up to huge numbers, right? Like you could just look them up. But I mean, the numbers they're using are just incredibly large. There's no way to have all the phi values tabulated for every possible product of primes when you get into the numbers that are 256 bits long. Right.
Well, and also just you don't even have to go to that big to get a large number. I mean, how many different ways can you multiply two primes out of, a set of 100 primes or something,
Right.
Well, I think we can figure that out. It's actually probably not that big. Is that 100 choose 2? 4,950.
Okay. Yeah.
But yeah, that's just 100 primes. You go up to, like a billion primes, and it's even higher, lower, I think.
But yeah, you're right. Once you know n, you could somehow calculate 5n and work it out.
Right. So that's where the whole thing could break down. But that's where, it's just hard to get 5n. Right.
That's why you use enormous numbers.
And this is the fear of quantum computing, right? Is that, or at least the fear that we all hear when you hear about quantum computing is that we could, if it could prime factor in a very short time for very large prime numbers or products of prime numbers, then you'd be able to figure out what two numbers made n, and then very quickly get the private key and be able to crack the message.
Exactly. Yeah. And in that Art of the Problem video on YouTube, they show a graph, a website, I don't know, and he types in a bunch of numbers and shows how long it takes theoretically to calculate both how long it takes to calculate the product, which doesn't take much time at all, and then how long it takes to prime factor the number. And you can see the product is pretty linear. Like the time it takes is linear with the size of the numbers, the number of digits in the number. But then the prime factorization is an exponential curve that just explodes when you start getting pretty big. And so the time it takes to do the prime factorization of enormous numbers, ends up being longer than the age of the universe once you start getting really large.
Yeah, I wonder, but that takes into account modern compute power.
Exactly.
Right, yeah.
Yeah, and I think there's 3 Blue 1 Brown has a video on how hard it is to basically guess the encryption in SHA-256, or I think it's just 2 to the 256. Like how big is 2 to the 256 essentially. And he goes through ridiculous lengths to demonstrate how big that number is.
Yeah, it's roughly 10 to the 77. Hey, did you know if you put in like a really big number like this into Wolfram, it tells you like how to name that number? So 2 to the 256, sorry, this is a random sidetrack, is 115 quattuorovigintillion 762 trevigintillion 89 duovigintillion. Like, I don't even know what these are. I didn't know. Why have people named this?
Yeah.
Like, okay, after trillion, quadrillion, quintillion, sextillion, septillion, octillion, nonillion, decillion. So this must just be like related to polygons.
And then it says the comparison is it's basically 0.1% of the number of atoms in the visible universe.
Oh yeah, wow.
But yeah, there's a 3 Blue 1 Brown video that discusses how secure is 256-bit security. And
then, I'm sure it's, like you said, it's going to take the age of the universe to try and figure this stuff out.
Right.
As long as you can't. Yeah, I do these. I wonder if these videos take into account, like, maybe that's just my computer running, but like, what if I get like a GPU with, all of its processors?
I think he uses like the best supercomputers like imaginable as his comparison.
Oh, okay.
Yeah.
So
that's RSA encryption. Fancy way to send encrypted messages back and forth. Took a long time to explain, but I think it's once you do it, it's really straightforward.
Yeah. So with Diffie-Hellman, you're talking to the right person. But I guess in some sense, with RSA, you don't have to be talking to the right person. You can just send your info out to anybody.
Right.
And only the person with the public key and the private key for the public key and the prime are going to be able to figure out what that message is.
Yeah. Yeah. You can just put your message out there on a website publicly and then only tell the person literally call the person on the phone and say like, hey, go to my website and decrypt this because you're the only person that can because I used your public key.
Right.
So you're the only one with the private key that matches it, so you can understand it. Nobody else can.
That's pretty cool. Wow, man.
Yeah.
You always hear of all these like crazy ciphers and stuff in like what's that movie with Nick Cage when he's gonna steal the Declaration of Independence. What's that movie?
National Treasure.
Yeah. Like I feel like and stuff like that, or the Angels and Demons, or whatever the other one is called. There's all these like fancy ciphers that they figure if only they knew RSA encryption, like.
Right.
Nick Cage would still be sitting there trying to figure out what the hell they're talking about.
Yep. Yeah. All right. Well, that was cool.
Yeah. I hope you guys followed along. That was a little math heavy episode, but pretty interesting, I think.
Yeah. It's simpler than you think. Like you imagine like RSA encryption. You're like, oh my God, my computer's got to be working so hard and doing crazy math. Like it's not really. It's just multiplication. That's kind of it.
Yeah, it's really big multiplication.
Yeah, but it's easy for computers to handle that.
Yeah, cool. Well, now we're going to start. We're going to release a public key and a prime number, and all you guys are going to have to encrypt it.
Send us secret messages.
You can send it to me at Zach with a K, Z-A-K, on Twitter, or
yep. I am at Like Tortilla, Derek Padilla, Like Tortilla. Cool.
And or you can send us emails at some email we have yet to publish.
hbar@thehyperfine.com.
Oh, is that it?
Yeah.
Okay. hbar, one word, no hyphen.
Yeah, no bars.
Yeah, if you can find the bar, that's good for you. Maybe if you had a Mac.
Yeah, you have to insert the symbol, the H-bar symbol.
It's our way of limiting the number of emails that we could get.
It crashes 98% of phones.
Yeah. Cool. All right. Well, I think that was a useful conversation and some insight into it. I've heard the Diffie-Hellman encryption a few times, but it's never quite clicked. But that was a pretty good explanation I was able to follow. So
cool. Awesome. Well, I will see you next week. Hopefully not with a cold.
Yeah. I hope you feel better.
Thanks.
Right. Bye.
See ya.